Alright guys, we got this last one this Sunday of the Labor Day weekend. Let's do it before church, guys. Okay, oxidation reduction. So last part is about acid, basic. We talk about what each of those are just briefly, and the reaction that comes after it, and then the different way to write strong and weak acid. And then we talk about how we draw the particulate diagram. And the second one we talk about carbonic acid or carbonic reaction. How it's like the same with our acid and basic, except you have one more byproduct, which is gonna be our CO2. And in that case, also the weak acids do stay the same, right? So today we're gonna be talking about oxidation and reduction. Reaction, oxidation reduction, also known as redox, is a reaction where there is a transfer. We're focusing on the electrons. So whenever electrons can move freely like this, we know that it's gonna involve a lot of our mostly metal, but I think a lot of metal too. We're looking at examples, but where metal's gonna allow them to go through a little bit more, but also non-metal form is element form, and yeah, it's just actually just open. But this is important when we talk about oxidation and reduction reaction, because we are chasing electrons. So a lot of times, right, I was looking at some of the examples, like, well, and they're just sharing electron, but it's for, in a sense, for formality's sake. So it's like a kind of convention where we just tell how does the electron go from one place to another, and in most of the cases it's going to be useful. Some of the cases it might not be, what was actually happening physically and chemically, but it's going to be useful for us to tell where the electron's going, which one is being oxidized, which one is being reduced, and which one is gaining, which one is losing electrons. So we can follow the chase, and at the same time, right, same with bonding. The only reason why they will receive and accept electrons is either two reasons. One is if additional energy is being put in there, right? So they're forced to take an electron because of the additional energy, or because it's more stable for them to receive electrons. So whenever they're usually more stable, they usually are gonna release energy out. Okay, so again, right, like we haven't really gone to the free energy, but you can see that most of the reason why we see reaction happen has to, it's just only a few of the reason, and most of them really tie back to our energy, how things right, how stable are them, right? If they're more stable, they tend to release more energy. Last part we talk about CO2 as a prime example of being really stable, right? And so therefore chemicals are gonna want to take that configuration with the oxygen double bonding with the carbon double bonding with oxygen, and during that time then you do release a bunch of energy, and we do use that, right? Fossil fuel is just a prime example how we use them, how we exploit and utilize the tendency for chemicals to do that to harvest the energy that we need. Now, on the other hand, right, how did they get so much energy in the first place? So they have to take million years pressure, so the energy ultimately going to come from the earth, pushing it down, and also having that heat supplied. So a lot of the redox energy is going to be similar as well. So if they do end up having to force to either give up or receive electron, that's if they have additional energy. So some of the most famous redox energy is going to be in your body, your cellular respiration. So you could see the electron transfer chain that happens in your mitochondrial cell, right? So that we're taking a high energy content, we're breaking it down. So that whole process is going to be pretty smooth, right? It's gonna want to move forward on its own. Then on the opposite spectrum, it's gonna be our electron transfer chains that happen in our photosynthesis in our chloroplasts, in the plants, not ours. So those you're gonna have to force energy down in order for different molecules to either accept electrons or willing to give up the electron. And of course, the energy gonna be our Earth. So a lot of times, right, we do talk about redox just because it's a good way to kind of keep track on where the electrons are going in a pretty complex change of reaction. So just bear with us if some of those are a little counter intuition. We'll work on this together, and you can ask me. So do you kind of know those 4 type of reaction? You should already learn those from our last year of chemistry about different reaction type. You have synthesis, means X and Y going together, right? They're synthesizing together to become one compound. Decomposition, it's gonna be just the opposite. You have something bond together, now you have them coming apart. Single replacement, right? It's gonna be similar, but they're not. I guess this is Z. Let's use Z, right? And then X is gonna replace our Z, making our Z the free agent. So kind of like double replacement, except you don't have the other part for the bond to, so it's just single. Organic combustion is gonna be our combustion reaction where you end up with H2O and CO2, 2 of the very stable molecule. Okay. So chemical reaction, oxidation refers to the process in which substance loses electrons. This can also be described as an increase of oxidation state. So, in your last year's chemistry periodic table, a lot of people mention about the oxidation state. Yeah, so this is what the tendency of, there's like only a few states for each of the elements, right? That's gonna be the common state of losing electrons. So this element will, will tend to lose like 2 or 5, right? They generally just only have like 2 or 3 states. The chemical reduction refer to the process which it gains electrons. So, in a sense, the way that I generally think about it is that they being reduced, right? When it's being reduced, it's more negative. So, yeah, it's the same case as again electrons. So a lot of the metal and non-metal ionic compound is going to be our oxidation and reduction, right? When they combine together, they lose and gain electrons. Oxidation reaction are accompanied by reduction reaction where another substance gain electron lost during the oxidation process. So you have our, right, the one that's gonna gain, the one's gonna lose. So again, the transfer electron, we're chasing where the electrons go from place to place, and then we could see a little bit of like how the energy state for each of the molecules are together. This reaction are known as redox reaction. So I do look at, there's many ways you could call it gaining and losing electron. What does it have anything to do with oxidation? Oxidation, we tend to think about oxygen, right? So apparently, right, this is how they used to make other chemicals to lose electrons is to react it with oxygen. Okay, and a lot of time that it's gonna go, right. So oxygen is gonna want to react, and again want to form our CO2, our trusty CO2. So then you could oxidize the different chemicals by using oxygen. Oxygen is a pretty powerful oxidizing agent. It does want to react, especially if you give them, desirable product, just very stable product like CO2. It's gonna want to react. And where therefore, the other one is gonna be, so that is kind of where the names come from, right? That you're being oxidized, right? So you know they were working with gas, you know, with, I think 18th, 19th century. That's kind of where the things come from. That and then that's has been the tradition, you know, for them to work with oxygen, and just trying to oxidize different chemicals to see what happens. So that's just kind of where the name come from. If that helps you remember oxidation, then hopefully that's gonna help. Oxidation, so you know, as I simply say, a lot of the things that we do loses 2 electron. My ion loses 2 electron, ion 2 plus. So any type of ionic reaction is gonna be our oxidation and reduction reaction. It's pretty good. This one, this was not magnesium, right? I'm gonna look it up what that was. But Mn2 plus losing 5 to become Nn7 plus. So if they could lose 5, then I'm pretty sure this is our transitional metal. Right, so they do have the d orbital, so it allows them to do something like this, right? Again, like, you know, of course, like if you lose like 7 plus, it's not going to be as stable as you are only losing 2 electrons, so therefore 2 plus. However, right, if you give them enough, you know, favorable conditions, so a good, you know, hit of energy, then yes, they will still do it. Right, but it's all just the interplay with energy and what is stable and whatnot. In oxidation number increase phosphorus by gain 3 to become P-3, so kind of like the charges we talked about. Chlorine will gain 2 to become chlorine minus, right? Because now you have 2 in our natural current carrying gas. Now the oxidation state was lower or reduced. Okay, so just think about it, become more negative because they gain electron. So a lot of our group 15, 16, 17 are gonna be pretty predictable in terms of how they lose their thing, also, or how they gain electron, how they, you know, being reduced. And also our group 1 and 2 are also gonna be pretty predictable in terms of how they're gonna be oxidized, right? And really the trouble begins when we're looking at elements that are in between those two groups. So if you look at the rules that you could do, there's 2 options of the rules that you could do to try to figure it out. So rule number 1, option number 1, oxidation element, right? If you have element, we gonna think that they are gonna be chemically neutral, even if they bonded to themselves. So we're just gonna assume that they are neutral, where they're not gaining and losing electron at their element state. Monatomic ion, so just one atom, right? One atom ion. So for example, Na plus Cl or copper 2 plus, whatever is gonna be the same as is charge. Right, so the charges kind of help indicate our electrons. So later on when we do Redox, we might have a thing called formal charge. So again, you know, it's just kind of, we'll talk about those as we go. So these are more our bookkeeping way to look at reaction, and it does help predict a lot of the stuff. That's help us explain the things too. So fluorine, strong one's only gonna have -1. It's compound, so every time you have fluorine, that you know that it's gonna be -1. This one's gonna be -3 because it's 3 fluorine. Oxygen is usually in -2, except when it's in peroxide. So in the peroxide form, right, you have the H2O2. In the peroxide form, hydrogen peroxide form, then you are just a little bit different. Again, right, like, why do they have some of those charges, right? It has to do with things being stable and how it's, like, you know, sharing electrons all work out, right? At the end of the day, right, like I said, it's gonna have to be our fundamental state of the different forces, right? And, you know, when we learn about free energy, you have to know that it's going to be more stable. That's the only reason why they would want to stay in that state and be fine with it. So there's always going to be exception when we talk about chemistry. And again, this is due to how the wave mechanic for the electrons work out, and just the interplay between the neutrons and the proton and electron. So those are gonna be pretty complicated. And if you do anything chemistry related when you go to college, I think third year you spend a year just in physical chemistry. So those are gonna really dive into those fundamental forces, and you get a much better understanding why the exception rules always exist. In our when we look at periodic trend, when we look at reaction, there's always going to be exception because of those forces that interplay with each other. But most of the time in the high school level, we're just recognizing pattern. So we're just recognizing the pattern and we're applying the pattern, and so there's rules that comes with it, but those are just patterns, right? Our forces is gonna be our more fundamental rules, but those get really complicated really fast. So it's got like engineer, right? You just recognize rules, you recognize formula, and you apply it for now, instead of really finding the theoretical understanding behind it. Hydrogen plus one in its covalent compound. Okay, so I was looking at this as like, well, Ch.4, like why is like the oxidation number for carbon instead? So in covalent compound, hydrogen is going to be treated as +1. And just recall, like covalent is always going to be sharing, right? So this is where I'm talking about, if they're sharing, then they're not really just having one electrons for hydrogen completely give them up to it. So later on, as we talk about bond hybridization, you could actually see there's like experimental data that you could find out where does the electrons gonna stay most of the time in our CH bonds. So you could look at that, but again, this is our bookkeeping to help us understanding where the electrons going. So for that purpose alone, we are treating them as +1. So some example, H2O and H2E. So this one, H is gonna have our 3- charge, right? Because it have gained 3 electrons from our positively charged, or from our hydrogen sort of gas. So right, our N is in group 15. Right, so most of the time when we work out the oxidation charge, so for 15 it's gonna want to gain 3 electrons, right? And then so that they do give them 3 electrons. So there's other ways you could do it. Honestly, I feel like, again, it's kind of like it comes down to practice. You form a type of intuitions when you look at different chemicals. Feel like, hey, this seems to be the charge, right? So you form intuition when you do that. But those are rules that you can follow. Oxidation number of free elements, so O2, O3, ozone, are always going to be 0. Oxidation of monatomic is always equal to the charge, right? So monatomic, just one atom. Fluorine compounds always assign -1. Alkalines always have +1. So we talk about group 1 metal. So lithium, sodium, potassium. Alkaline group 2 always assign. So group 1 liquid is always going to be easy to find out. Right? Same with the solubility. We know that for sure group 1 is, right? And a lot of group 2 are going to be soluble in the water as well. Oxygen almost have -2 except in peroxide, which is, or when it's fluorine, when it's +2. So, yeah, a lot of exception about, different things. Fluorine is going to be an interesting element as we look at periodic trend. You can see the why is it special. Hydrogen have oxidation number of +1 compared to non-metal, but it has a -1 when combined with metal. Just remind about those. So it is an interesting one. It's right at element number 1, and most of our periodic table does color it as non-metal, but you know, just because how it's placed, it's gonna exhibit some of the property of both. So, right, again, always exception to the rules. The algebraic sum of oxidation has to be equal to 0. So, right, you cannot have like just one extra electron out of nowhere. Right? They all have to be accounted for. Oxidation state should be equal to the charges of the ion. So I'll give you a minute. Try to work on this on your own. You could pause if you could. So I'm gonna check as we go through each of those to make sure I don't get them wrong. But when I'm looking at SnCl4, immediately I have saw Cl, and my first guess is that Cl is gonna be our -1. So each one is gonna be -1, and you have 4Cl, so +4. So is that one of the rules? So monatomic. Yeah. So, you know, if you have last year's, then oscillator's number is going to help give you a clue as well. So look at that, then we look at calcium, right? Our metal 2 is going to give us a +2. So if we're 6 + 2, then we know this is 3 minus. So far it's still kind of conform to kind of the charges rules that we know. Right, basically what I mean is each of the calcium give up 2, and together the phosphate have received 6 of those. I'm gonna check periodically just to make sure I get those right. So again, SNO, so O is this not is this anything that is weird. So I'm gonna look at the notation to see if it's okay to write 3 minus or -3, you know, for our oxidation number. So I think charges, you do write, it's okay to write both. But I'll double check. So you know, remind me if I do forget. So then this is gonna be our +2. Okay, so silver, I know that most of the time it's gonna be +1. So, and then so the other one have to be -2, and it does matches so far as group 16, right? So I'm gonna double check to make sure I'm right. So so it is hydrogen in this case is bonded with our iodine, so this is a non-metal. So hydrogen should have a +1 charge, and iodine should have a -1 charge. N2H4, so it's bonded to our non-metal, so it's gonna be plus. Our hydrogen is gonna be +1. So then you have 4 + 1, right? So you have 4 plus, and you have 2 nitrogen, so each of them will take 2. Right? Yes. So this is a good case to look at. Hey, like it's not gonna be always gonna be the same as the ones that we could predict, but work off of things that you know for sure. Like hydrogen ain't gonna be able to give off 2. Right? Hydrogen only have 1, so you could either receive 1 or give off 1. So like you always have that guarantee, and then you can kind of work backward to find out what's the other one have to be, right? Otherwise, like this is in group 15, it should be -3, right? But it's not. You only receive the 2 electrons, right? As long as it's stable, it's fine. So that's all. Again, right? It has to be as long as it's stable. So this one, right? Work on oxygen is gonna be -2, right? Again, oxygen is gonna be -2, except in very special circumstance where you have 6 negatives, so it's gonna be +3. Okay, so S8. So sulfate in its form, my bond one is gonna be 0 because it's element. Again, so oxygen as well. Any more elements? So that's 2, right? Those are 2 elements that you have. So in this case, NO3 is gonna be a non-metal, so it's gonna happen to be +1. And O2 always have to be -2. So then you have -4 from the oxygen and +1 from the hydrogen. So to balance it out, it has to be +3. Yes. Okay. So our proton. So I'm gonna look into this as well. So when we draw like a proton out for acid, do we draw like H3O or H plus? So Just remind me if I do forget. I try to remember, but you know, it's Sunday on a Labor Day weekend. So in this case, we're gonna treat oxygen as also 2 minus, and then we do have 1 plus charge for the whole ion. So our if we have 3 of them, yeah, so it's gonna be +1 to get to 3 charges. There we go. Okay, again, oxygen -2, and then ClO, so our O -1, oxygen -6, so -5, so it's +5 to get to that charge. So in this case, you can see Cl are gaining 5 electrons. So it's group 17 has 7 valence electrons, so it's gaining 5 electrons. So, but this is like, you know, in a sense, it shows like how powerful oxygen is. So Cl is much better giving the electrons to oxygen than, you know, to gain them themselves. And this is our, if you have the H, right, that's our hypochloric acid. So just kind of, you know, recognize some of the forms. Again, it's gonna be -2 for oxygen. So sulfur in this case, so we're -6, but the overall charge is -2, so we have -4, and then we split it between 2 sulfur, so it'll be +2. Yeah. So this one's gonna be interesting. So K always gonna be +1, oxygen always gonna be -2. So work those out, -8, +1, so you have +7. So Mn, the tertiary metal, is gonna be a little bit tricky. Work them out, you wouldn't know them. Ammonium. So I see that for solubility charge, right? We know that this is a polyatomic ion, so it's gonna have to have our +1 into here. So let's split them out and work it out. But we know SO4 is gonna be 2 minus. So we know this is gonna be +2. I'm gonna try to see if it's right first. So we're gonna have our -8, and then we have -2, so it have to be +6 then, right? It have to be 6. Able to reach 6. So NH4 is gonna be positive for as a whole. And each H is, since it's bond to N, it's gonna be +1. So N is have to be -3. So the only one I'm not sure is the sulfur, if it's +6. Yes, it's gonna be +6. Okay. So if you need additional practice, please work on those, and you can ask me during class then. And another way to think about is oral rate. Oxidation involves loss of electron, reduction involves gain of electron. Or the way that I used to think about it is just reduction is always going to be you're reducing the number, so it's going to be more negative. And then oxidation is going to just be the opposite of the reduction, right? You only have 2 choices. But now you understand why, right? Oxidation means that you're using oxygen and oxidizing it, right? In the old time. Now enough isn't necessary. In the old time, so that, you know, so that oxygen will pull the electron. Therefore, whatever things that you're reacting with the oxygen are gonna be losing the electron. So many ways to think about it. It's just one way that works best for your brain. Determine species oxidized and reduced in the chemical reaction. In the example problem below, structure determine oxidation state of every species of the reaction first. So it's good. So this one's gonna be 0, right? Right off the bat, H2 is element. It's gonna be 0. So also, our sodium is also gonna be 0, because it is in its element form. Okay, so HBr, Br is gonna be our non-metal. So our H is gonna be at +1. Br then has to be at -1. Bromide, sodium always gonna be +1, -1. And identify the atom oxidized and the atom reduced. So identify type of reaction. Let's do that first. So sodium replaces this, so it's gonna be our single replacement reaction. Oxidize, so it's just to follow the charge, right? So H is our +1, and now is 0. So H's are the ones that are being reduced. then which one is being oxidized? Oh yeah, so atom being reduced right here. So then where does that electron come from? Well, obviously it has to come from sodium then, right? Sodium gain 1, so sodium is gonna be our oxidized element. So sodium gain single replacement, the charges work out. Okay. Direction: identify the type of reaction, identify the element and the atom reduced for each of those. So I'll give a pause. Pause this if you don't want to answer, and then work on your own. So this one is gonna be our synthesis reaction, because they go from, right, XY to XY and chemically bond together. For that one, again, we're looking at our replacement, like so it could also not replace the metal, but the non-metal part of ionic salt, that's fine too. So that's gonna be our single. We're replacing just a single, not a double replacement reaction. So let's just find the oxidation state. Ion is always gonna be 0 in its element form. So in this case, then right, our oxygen is gonna be our reducing agent, and our ion is gonna be our oxidated. So here you can clearly see why does it cause oxidated, right? Because you literally react with oxygen. And right, with a lab that we did with the magnesium oxide, you know that they wanted to react, wanted to be oxidized. So they just need a little bit of heat, right? Not actually not just a little bit heat, quite a bit heat to get that going. So for this one, chloride is its element form is 0, boron is element form is 0. In this case, boron is going to be -1. This is going to be +2. Right, we talk about rules. How about group 2 is always going to be +2. So +2. I don't know if it's rule, but whenever I see halogen metal, so halogen non-metal, so 17, I like most of the time I assume it's going to be -1, except for like fluorine. Fluorine's a special case. So in this case, right, chloride went from zero oxidation to -1, so that one is gonna be reduced. And our calcium in this case our bromides go from +1 to 0, so our bromide is being oxidized. So do you notice this one does not include oxygen in there, right? Again, like oxygen being oxidized was the tradition, and then they just kept it ever since. Synthesis, single replacement, ions being oxide, oxygen. So boron oxide is being reduced, right? Yeah. So mention those to get your full credit. So practice free response questions. Copper plus 2 silver NOH plus copper NO3 2 plus silver. So silver nitrate, copper nitrate. I guess like I could say the name out. When I was in high school, I'm never good at names because I'm never good at English. So I always just say the formula out. But I guess I could try to do a little bit more. Cleanness CU is being reduced. Do you agree, disagree? Just your answer in terms of oxidation. So basically, they want to find out the oxidation. So this is 0 right at first. 0 first. Nitrate, we know that it's going to be -1. Silver going to be +1. Copper, right, you have 2 -1, so +2 in our case. So our copper go from 0 to +2, so copper is going to be oxidized. Sorry for if I misspell anything. Then our Ag is going to be reduced. We're going +1 to 0, so it's been reducing the number. So in case no, right, we disagree because copper start with 0 oxidation number, and after the reaction, so after reaction, copper has +2. So it was oxidized, not reduced. Okay, so you have to mention the evidence, right? You have to mention your claim first, right? You have to give your evidence, and then just kind of tie it all back with your reasoning. Disagree, loses, oxidation 0 to 2 not being reduced. So I guess, right, mentioning this will be good too. So do mention the Ch.4. So, right, so you could also talk about which one is being reduced. So once you go from that, then we know the other one has to be oxidized. Okay, identify the species that was reduced in this titration reaction. So we'll be working with titration pretty soon. I think next unit is acid and base it. And then justify your answer in terms of oxidation. Yeah, so we'll just work it out. So obviously we saw that, right? So it's going to be +1. So it meaning that it lost this 1, right? So, you know, indicated as charge. Something else right here, right? 2 plus. So those are the easiest one to do. H2O, +1, right? -2, those are easy. I guess -2, then +4, meaning our carbon loses 4 electrons. So this one, you just work, right? This one's gonna be +1. Right, hydrogen is bonding with non-metal, so it's always gonna be +1. Oxygen is always gonna be -2, and that's a special case. So -8, right? +2. So you're gonna have our so we're gonna have -6 that we need to balance out, and then so each one is gonna be +3. So notice that I noticed right off the bat the carbon are not the same. So let me double check to see if it's right first. Okay, so it doesn't really talk about carbon at all. Yeah, let me look at the note. Oh, I don't want to look at the note right now because I need to erase my notation. So we'll look at the note in a bit. So this one, -2, so you have -8, but you have a -1 charge, so you have -7. So this one's gonna be +7 in order to balance it out. Okay, we have all the oxidation number. Let's check them out, right? So H's always stay the same. Oxygen always pretty much stay the same, and that's what we kind of set up to find out those. So in this case, our magnesium is gonna be, or not magnesium, Mn is gonna be reduced, and our carbon are gonna be oxidized. So we have, yeah, but notice they have to balance out, right? So we have 2 Mn that is being reduced, and each of them are gaining 5 electrons. So in total, we 10 of them are being reduced, or 10 electrons are being gained by our Mn. So then we also gonna have to have 10 carbon, right, to give up 1 electron, and we do have 10 carbon on each side. So, you know, they have to balance out as well. So justify my answer in terms of oxidation number. So we did identify the species that's reduced. Yeah, so we just talk about Mn. Start at +7 is oxidation number, and you know after the reaction, you end up with +2 oxidation number, telling us that it gained 5 electrons in the process. So, and then therefore the one that being reduced. Good. Amazing. +2. Amazing. Easy. Okay, so part to identify the reaction above us. Oh yeah, we're identifying the acid reaction. I think this is like the actual question that the author graded. So it's from 2023 free response. Let's go ahead. So right up, I do notice water and carbon dioxide and our weak acid here. So then, pause. Based on those, then what do you think it is? It's gonna be, yeah, so possible. It's gonna be our pseudo acid and basic reaction, right? But we're gonna still call it acid and basic reaction. Let me make sure that is correct. Yeah, acid base. So because when we acid, and then we could see the water is a clear indication of those coming back together. So we have to justify our answers. So what would I say? So just what I say we'll start with weak acid. So our ethanol acid is gonna be our weak acid, or our vinegar is gonna be our weak acid, and then we do have our weak base. So our sodium hydro carbonate. So our sodium bicarbonate, baking soda are gonna be our weak base, and together they do produce water, right? Which is our product for neutralization, right? Because so far we are just describing right here, from here to here, we're just describing the reaction. So we have to kind of talk about is the product for neutralization, right? Giving me, right, letting us know no acid and basic reacted, right? Along with the fact that we do have weak acid and weak base to start with. So that's what I would say. So let me double check if it's correct, because I'm never really good with explaining stuff. I always get dot point for doing that. Okay, so we acid, the weak acid react with the weak base, with the with our ethanol acids donating a proton. So I guess we want to mention the fact that it does donate a proton and form and react with, probably also mention the OHs that come from our baking soda to form H2O. So saying that is probably going to be better, right? So that is going to be part of our net ionic, because so saying that part of the reaction, I was going to make sure we secure that point. Again, so no solid, so it's not a participate, and none of them change. So you could do the negative, right? So you could rule them out and then say, hey, like, those are, if that's the case, then, those are the things that, yeah, if that's the case, right, then you're only left with one answer. So there's two ways to go about it. I think probably the first way is going to be straightforward. So identify the weak acid and bases, and probably identify which one is the donor and which one is the receiver, and the product, which is H2O. That's fine. So I was able to identify the product, but I wasn't able to articulate the the proton donation thing. So keep those in mind. What's this? So involving organic combustion, organic formula refer to carbon-based molecule combined typically with hydrogen and some of oxygen, and then being burned with oxygen gas to result in a product of carbon dioxide and water. So when we're doing combustion reaction, our product always going to be carbon dioxide and water. This is with any combustion, right? The clear you could have, the clear fuel you could have, that's, if you only have those two, when you burn a fuel, fossil fuel, that's, then you call it clear fuel, right? But most of the time, when you burn our gasoline, you're come up with a host of different byproducts. That's why you have our catalytic converter, which have precious metals, so like platinum and other metal that help at us our catalyst to kind of convert those really toxic gas into more useful gas. So that's why California has one of the strictest air emission regulation. So that's why California have a lot more catalytic fee, because the catalytic oil converter have to be pretty strong. And this is also why when you have natural gas vehicle, so a methane vehicle, propane vehicle, they are called clean burning gas, because you only have methane, right? Instead of like gasoline, you have a host of byproduct. Or methane, you only have methane. So those are what we call clean reaction, because there's no other byproduct. So a lot of bus, right? CNG, compressed natural gas, CNG buses. There's a few cars that also commercially available for CNG. Honda Civics was one. So I never knew why they don't get popularized, because it's a little bit cheaper and it's supposed to be more green, right? So I don't know why it doesn't get popularized. It does get popularized in public transit, and also with like truckers. Some of the trucks use CNG, but not commercially for whatever reason. But then I guess I'm not surprised, right? We also have hydrogen fuel with the Toyota Miria, but it was just never popularized or popular, not as popular as in Japan for whatever reason. So, making clean alternative fuel that is, cheaper and stuff, does not always equal to commercially successful. So, those are two very different things. So for those who are studying business, that's the key. Right, since the oxidation of what are we trying to do? Yeah, since the oxidation of oxygen is changed from zero, right, because it's an element, Th2 is being reduced, carbon is being oxidized. So, right, again, the oxygen are being the one that's taken away and, being the leader of our reaction in this case. So if oxygen oxidize or reduce, so, right, I mean, it's just like the same thing that we have been doing the whole time. So most of them are going to be -2, right? But for the 3 oxygen gas that we have is being reduced. So I would say that, right? So I would just state the obvious. So the 3 oxygen molecules in element form reduced it from 0 to -2. Yeah, so I guess you could say like therefore oxygen was reduced. Obviously, like not the oxygen in our, I don't know what chemical is, C2H5, OH, but our oxygen in here is being reduced. Since oxidation is changed from 0 to is a reduction. Okay, this is it. So for parting words, we'll see how this go. I'm not sure. I think it's a little bit more work on your side, to do the flipped classroom model again. But ultimately, I think it's gonna benefit us as a class more. We have more, like, people got adjust their pace. I have more time during class instead of just talking, to really, go to each of you guys to kind of figure out. Because I don't know, you guys are the class, I don't completely know everybody's name yet, because I wasn't able to keep calling on everybody. So it will give me a chance to really just, have those individual time with each one of us. And we could do more like group work. We could do more labs. The labs that we did last time took the whole class, right? If you want to do more labs, and then we also have to do this. We also have to do review and test review. I mean, we can't do all of that. So give or take, right? And my give is, I'm not gonna want to lecture during class that much anymore. And we will take back more of the stuff that we could do outside of lecture. That's kind of what I wanted to do. Okay, I know there's a little more work on you, but you guys signed up for AP Chemistry, so yeah. Okay. This is it for me for this unit.